Good evening, everyone. So, welcome to my YouTube channel, Maths Avtaram. So, today we are going to see first lecture on linear transformation. Today we will see what are the linear transformation. Okay, and we will see some of its example and which are not linear transformation. We will check it. Okay, linear transformation. Let V and W be two vector spaces over the same field F. Then a map T V to W is said to be said to be a linear transformation if T alpha times B1 plus beta B2 is equal to alpha times T B1 plus beta times T B2 for all B1 B2 belongs to B and alpha beta belongs to field F. Okay. Note that a linear transformation is also called linear map. Is also called linear map. Okay. So I am going to prove a result. Let V and W be two vector spaces over the same field F. Then T V to W is a linear transformation if and only if T V1 plus V2 is equal to T V1 plus T V2 and T alpha times V1 is equal to alpha T V1 for all V1 V2 belongs to V and alpha belongs to field. Okay. Let's see its proof. First, assume that T V to W is a linear transformation. Then T alpha B plus B T beta is equal to alpha T B1 plus beta T B2 for all alpha beta belongs to F and B1 B2 belongs. Take alpha is equal to beta is equal to 1. Then T B1 plus B2 is equal to T1 V1 plus 1 V2 is equal to 1 TB1 1 TB2 is equal to TB1 plus TB2. So this implies TB1 plus B2 is equal to TB1 TB2. Next, take beta is equal to 0. P cat T alpha B1 is equal to T alpha B1 plus 0 B2 is equal to alpha TB1 0 TB2. So TB1. So this is alpha TB. So this implies T alpha B1 is equal to alpha T. Therefore, TB1 plus B2 is equal to TB1 plus TB2 and T alpha B1 is equal to alpha times TB1. For all B1, B2 belongs to V and alpha belongs to K. So we got this one. One direction is proved. Okay. Now conversely, assume that suppose that T V1 plus V2 is equal to T V1 plus T V2 and T alpha times V1 equal to alpha times V1 for all V1, V2 belongs to B and alpha beta belongs to K. Okay. Now T alpha B1 plus beta. Okay. So what will be this? This will be by this property. You consider alpha B1 is equal to B1. So by first property, this one we have alpha B1. Okay. Now using second property, what we will have? This implies T is a linear transform. So properties of linear transformations. Let V and W be two linear transformations over the same field F. Then if T V to W be a linear transformation, then first T takes zero element to zero element. Second, T minus V is equal to minus of Tv. For all B belongs to V. Third one, T V1 minus V2 is equal to T V1 minus T V2. So proof. First one, T 0 is equal to T 0 plus 0 I can write. But this is equal to T0. This implies what but this is equal to T plus this is cancelled. So this is proof. Second, P minus B. This is nothing but minus 1 B. So minus okay. Third, so this is also proof. Example, R square and R are vector spaces over R. Define T R to R by T x y is equal to x. Is T a linear transformation? Let v1 is equal to x1, y1, v2 is equal to x2, y2 belongs to R, and alpha and beta belongs to M. Filled. Then T alpha v1 plus beta v2 is equal to T alpha x1 y1 beta x2 y2. But definition of T, first coordinate will come. But what is this? So this implies is a linear transformation. Example 2. R2 and R3 are vector spaces over R. Define T R2 to R3 by Txy is equal to x plus y, x minus y, y is T a linear transformation. Let v1 is equal to x1, y1, g2 is equal to x2, y2 belongs to R2, and alpha beta belongs to R. Then T alpha b1 plus beta is equal to T alpha x1 y1 plus beta x2 y2. So this is T alpha x1 plus beta x2 alpha y1 plus beta y2. This is alpha x1 plus beta x2 plus alpha y1 plus beta y2 alpha x1 plus beta x2 minus alpha y1 beta y2 alpha y1 plus beta y2. Then I can write it alpha x1 plus x2 plus beta y1 plus y2 alpha x1 minus x2 plus beta y1 minus y2 alpha y1 beta y. So how can I write this? Alpha x1 alpha x1 minus x2 alpha y beta y1 plus y2 beta y plus y2 beta alpha x1 plus x2 x1 minus x2 y1 sorry it is so this is here alpha y1 this is x2 this is y1 this is x2 so this is alpha x1 plus y1 alpha x1 minus y alpha y1 plus beta x2 plus y2 beta x2 minus y2 beta y2. So this is x1 plus y1 x1 minus y1 plus beta x2 plus y2 x2 minus y2 y. So this is t x1 y1. This is t x2 y2. This is t v1 t v2. So this plus t alpha b1 beta b2 is equal to alpha t v1 plus t v2 for all v1 v2 belongs to v and alpha beta belongs to r. So this implies t r2 to r3 is a linear transformation. So R square is a vector space over R. Define T R square to R square by T x y is equal to x y. R square and R are vector spaces over R. So we are defining this now. Is T a linear transformation? Solution. V1 is equal to take this one. Now T V1 is equal to 1 into 0, 0 and T V2 T V1 plus V2. So this implies T V1 plus V2 is equal to 1. This is not equal to 0. That is T V1 plus T V2. So this implies T V1 plus V2 not equal to T V1. So this implies T is not a linear transformation. Example 4. R square is the vector space over R. Define T R square to R square by Txy is equal to x plus y plus 1, 0. Is T a linear transformation? Solution. T 0. What is this? T 0, 0. So it is 0 plus 0 plus 1. That is 1, 0. Which is not equal to 0, 0. It means 0. So this implies T0 is not equal to 0. So this implies T is not a linear transformation. Because every linear transformation takes 0 to 0. We have shown it already. Example 5. R square and R are vector spaces over R. Define T R square to R by Txy is equal to mod x minus y. Is T a linear transformation? Solution. Take V is equal to 2, 1. Then T minus V, that is T. Notice now what is TB? TB. So this implies minus TB is equal to minus 1. But so this implies T minus T also. So this implies T is not a linear transformation. Example 6. R, Q, and R are vector spaces over R. Define T R cubed to R by T x y z is equal to x plus y plus z. Is T a linear transformation? Solution. Let B is equal to x1, y1, z1, and B2 is equal to x2, y2, z2 belongs to R2, and alpha and beta belongs to R. Now, T alpha B1 plus T V2 is equal to 3 times alpha x1 z1 plus beta x2 y2 z2. So what is this? Alpha x1 beta x2 alpha y1 plus beta y2 alpha z1 plus beta z2. So this is alpha x1 plus beta x2. This is my x coordinate. This is my y coordinate. And this is my z coordinate. So write this alpha x1 plus alpha y1 plus alpha z1 plus beta x2 beta y2 beta z. What is it? This x1 plus y1 x1 plus y1 plus z1 beta x2 y2 plus z2. So what is this? This is nothing but 2x1 y1 z1. This is x2 y2 z. So this is P v1 beta P v2. So this implies P alpha v1 plus P v2 is equal to alpha T v1 plus beta T v2 for all alpha beta belongs to R and v1 v2 belongs to R cube. So this implies P is a linear transformation. So this is up to this. So today's lecture up to this. If you have any comments related to this, you can comment on my YouTube channel. Like, share, comment, and subscribe my YouTube channel. So thank you very much for today's lecture. Thank you very much. We will see you for next lecture.